A very good morning, sir. I am Mohammad Hani from CSCB section, and for the presentation, my topic given is bipolar junction transistor BJT CB configuration, that is common base configuration. So, coming to the outline of the outline of the presentation consists of introduction to the topic, that is BJT, representation, working principle, and some derivational part, characteristics, advantages, disadvantages, applications, and comparison of BJT common base configuration with other configurations, and finally conclusion. Moving on to the next slide. Introduction to bipolar junction diode CB configuration. The CB configuration stands for common base configuration in bipolar junction diodes. In CB configuration, the base terminal of the diode is common between input and output, in which we will look into the further slides and we'll get to know this about this point. This configuration offers high input impedance and low output impedance. Representation of BJT CB configuration. So you could see here a diode is taken, a transistor is taken where this left side is called as like COM E, B, C, emitter, base, and collector from the other side. So the current from E is called as is taken as IE, and the current that is coming to the C is called as IC, that is collector. And down here the base is common, like between E and C, that is between emitter and collector. There is a common base connected to the some voltage. See here, uh, the left side is input signal and right side we get output. So in input signal we have to give forward bias, and output signal we have to give the reverse bias. So for forward bias, NPN transistor, negative negative, it becomes this negative becomes the forward bias, and here the positive negative side is connected to the positive, so hence this is called as um, reverse bias. Now let us move on to the working principle of bipolar junction diode CB configuration. The input signal is applied to the emitter terminal and the output is taken from the collector terminal. See, from left side, as we have seen in the diagram, from the left side we are providing the input signal, and from the right side, that is um, from the collector terminal, we are collecting the output signal, and the base terminal acts as a common connection point for both input and output signals. As we can see in the diagram, it is placed in between the input signal and output signal. CB configuration provides unity current gain and phase inversion. Coming to this point, we'll prove this in the derivational part in the next slide. So finally, we have come to the derivational part, and see, as you could see, the diagram is perfectly drawn here. NPN transistor, where left side is emitter, the right side is collector, and down there is a common base. And you could see in the left side it is um, forward bias, and the right output side it is reverse bias. See here, it is written clearly, and the current it is left side is called as IE, that is input signal, and output signal it is IC. And since it is common base, IB current is here. IE current is flowing this words, and for example, if you take this node, according to Kirchhoff's law, sum of currents entering is equals to sum of currents leaving the node. So it is called IE is equals to IB plus IC. IE is equals to IB plus IC. We have got a relation, and for this purpose, and now we will derive the DC current gain. So basically, DC current gain we have taken, like it is the ratio between the collector current to the emitter current, and hence we need IC, the collector current. It means we need output current. It is like cross multiplying alpha into DC into IE. Let this be let us keep this equation aside, and we'll move on to the AC current gain. Coming to the AC current gain, basic definition of AC current gain is alpha AC is equals to ratio of change in collector current to the change in emitter current, and hence we get alpha AC is equals to 1 minus delta IB by delta IE. We have to prove this. So for this, we already have IE is equals to IB plus IC. So here it is change in currents, because that's why we take deltas. Delta IE is equals to delta IB plus delta IC, and dividing the entire equation by delta IE. So here delta I gets cancelled and it is unity and is equals to delta IB by delta IE plus delta IC by delta IE. And according to this equation, here we have delta IC by delta IE as alpha AC. So we put alpha AC here. And finally, we need the AC current gain. So we put alpha AC is equals to a side and at the other side 1 minus delta IB by delta IE. So this is a simple derivational part for the BJT, that is bipolar junction transistor common base configuration. Now we'll move on to the applications of bipolar junction diode CB configuration. CB configuration is often used in high frequency applications due to its high frequency response. It is commonly used in RF amplifiers, oscillators and mixers. CB configuration is also suitable for impedance matching circuits. So basically the CB configuration is like required for amplifying the current. See, for example, if you provide um, 5 uh, 5 amperes of current, and in the output we are not getting 5 amperes current, we are getting more than 5 amperes of current. Like if, for example, if you take 10 amperes of current, see here, it acts as amplifier which amplifies the current. Talking about the advantages, the CB configuration provides high frequency response and stability. You see in CB configuration, you could see more stability, and CB configuration offers good isolation between input and output signals. And for justifying this point, we could see the diagram that the base is between emitter and collector. So this is the reason why it provides good isolation. The input capacitance of CB configuration is low compared to other configurations. Coming to the disadvantages, CB configuration has low voltage gain compared to other configurations. In the sense, it cannot accept more voltage as input current. And the power gain of CB configuration is limited. That is what we have discussed so far. And it is not suitable for applications requiring high voltage gain. Comparison with other configurations. So now we are going to compare the CV configurations with CE configuration and CC configuration. CE is common emitter and CC is common collector. Since my topic is CB configuration, I'll be discussing about CB configuration. See, the common base configuration has a higher bandwidth when compared to CE configuration, and CE configuration offers higher voltage gain compared to CB configuration. See here, the voltage gain is provided more by the common emitter configuration rather than common base configuration. And common base configuration has lower input capacitance compared to common collector configuration. So moving on to the conclusion. In conclusion, bipolar junction diode CB configuration is a common base configuration that offers high frequency response and stability. In BJT, in common base, especially common base configuration, we could actually see more stability. The reason behind this is like the base is present in between, exactly in between the emitter and collector. That is the reason why it offers higher stability when compared to other configurations. And while it may not be suitable for applications requiring high voltage gain, CB configuration is widely used in RF amplifiers and other higher frequency circuits. And we have also discussed about disadvantages, that it is not able to support higher voltage gain. But even though it is used in some amplifiers where input current is given in a limited uh, voltage and output is also like amplified, increased. And coming to the last point, understanding the characteristics, advantages and limitations of common base configuration is crucial for success, design and implementation in electronic circuits. So in this way, the BJT, the bipolar junction transistor common base configuration works. I hope the topic that I have given the presentation is clearly explained, and thank you for your patience listening.